Okay, this lecture is over Chapter 5 entitled Dynamic Routing. The main topic of this course is routing, which of course is getting packets correctly from their source location to their destination. And the dynamic refers to the fact that over time, either because of topology changes or links going down or links getting slow, that the route that the packets may take, i.e. the routing tables, may change over time. So this chapter is going to talk about dynamic routing and talk about a number of different routing protocols that we might encounter when we're looking at a network. The next page is an activity. It's called How Much Does It Cost? And is trying to introduce you to the concept of there is a cost or a delay or something like that when we send packets based upon the route we choose. So this is an activity that is intended to do with your classmates. You don't have to actually do the activity unless you want to grab some friends or roommates or something and go through and do it if it makes it a little easier. But basically what I want you to do is I am going to assign activity 5012, and you will just read it and then answer the reflection questions that are at the end of that. So there are a number of ways to classify routing protocols depending upon what we're looking at, and this table or this chart introduces us to a lot of them. So at the top we have dynamic routing protocols, which of course is the topic of the chapter. There are a number of purposes of routing protocols. One is to do the discovery of remote networks. Two is to maintain up-to-date routing information tables. Three is to, when sending a packet, choose the best path to destination networks for the packet. And fourth, to find new best paths when the current path no longer exists or some characteristic about the network changes that would affect the routing decisions. So we're going to discuss everything at least once, if not twice, that's in this table, but we'll just go over it real quick. Routing protocols can be declared either interior gateway protocols or exterior gateway protocols. Briefly, interior gateway protocols are basically routers within the same cloud. Exterior gateway protocols are routing protocols that are used between networks or between clouds. So that's one way to classify them. If we move down to the middle row, there are ways to classify it based upon how routing decisions are made. That may be distance vector, which is how far the packet is going to travel if it takes a particular route. Link state, which is what is the condition, the speed, is it up or down, how fast, how slow is a connection, and then path vector routing protocols, which deal with a path, a complete path from the source to the destination. As far as distance vector, there are a couple of those. There's RIP, which stands for Routing Information Protocol. There's version 1, which was the original, and then version 2, which is the current. We'll talk about some enhancements and changes that were made. We have IGRP, which is Interior Gateway Routing Protocol, and then we have Enhanced IGRP that came about later. If we look at link state, we have Open Shortest Path First, OSPF. We have IS-IS, which stands for Intermediate System to Intermediate System. And then as far as path vector routing protocols, VGP, Border Gateway Protocol, is the one we'll talk about there. So between IGP and EGP, So what they're showing you is within the clouds we have different interior gateway protocols, OSPF, RIP, ISIS, and then between these clouds we have VGP everywhere, which is an exterior gateway routing protocol. Okay, you can read the information over to the right. I don't see anything that sticks out right now. As far as distance vector protocol, basically what you can think of as the distance as far as being the number of hops to make it through the, how many routers does it have to go through to get to the destination gateway, basically. And then the vector implies direction. And in the case of routing, it's basically the direction is what port does it have to leave on the router to make it to its next hop or possibly the destination network. Here are 4 of the popular distance vector IGPs that we talk about for IP version 4. There's RIP version 1, which has been deprecated. There's RIP version 2, there's IGRP, and there's enhanced IGRP. And basically they have some information like IGRP is considered replaced by eIGRP these days. Okay, as far as this one, I first want to play the animation. Again, link state deals with what is the status or the state of the various links, which could also be called connections. So if a link goes down, the router that notices that is going to send updates to the rest of the topology so that all the routers in this case know that the connection to the 172.16.3.0/24 network is unavailable. So over here in the bottom right, they tell you some things. They say link state protocols work best when the design is hierarchical, which is kind of like an upside down tree where you don't have a lot of redundancy and crisscrossing of connections. When you need to know very quickly about changes in your network, link state protocols or routing protocols are good. And the administrator needs to be knowledgeable about how to set these networks up and run them for them to work efficiently. The 2 major link state IP version 4 interior gateway protocols we have is OSPF, again, open shortest path first, and ISIS, which is intermediate system to intermediate system. Okay. This is talking about classful routing protocols. It may be a while since you've heard the term classful, but classful refers to about how IP addresses were allocated originally. If the IP address started with a 0, that would give us networks 0 through 127. That was called a Class A network. If it started with 1-0, then it was a Class B network, etc. So you had Class A, B, and C, which we assigned devices, and then you had D and E also. So that's classful. So based on the IP address, we know that either the first octet, the first 2 octets, or the first 3 octets are the network portion. So in the case of classful networking, you do not need to send the subnet mask because that can be figured out from the beginning of the IP address. So in this case, we have a router which a timer expires, and it's running RIP, so it needs to tell its neighbors information about the network. So it's going to send out an update. When that happens, in this case router 2 sees it and it records that information. Also gives some timing information and tells what connection it saw that update on. Now then, if we have another router, router 3, that's going to expire its timer, it's going to need to notify its RIP neighbors. So here we see that we have an update that came in over serial 001, 14 seconds ago. And then finally, from router 2, we're pinging a particular IP that's going to be over here. So we're just showing that we have the pings going through and working correctly because the routing tables are up to date. Now then, the opposite of classful routing is classless. And basically the brief description of classless routing is, with the exception of we have to have 2 bits at the beginning and 2 bits at the end of the IP address to be either in the network or host portion, we can do the division between the network and host portion of the IP address anywhere we want. So if we're using classless routing, then we are going to send the subnet mask information with it. So we're going to have basically the same thing here, router 1. The only difference is we're doing classless routing. Router 1 is going to send out an update, and when it does that, just like before, router 2 sees it and records the information. Notice that this time in slash or CIDR notation, we have the /24. So even though this is classless, this is behaving like a Class C network, where the division is at the 3rd decimal point. Then what happens is this router expires, it sends its information, and again it is updated in this case in router 2. So router 2 has a complete representation of what the network is. And then here in the last one, again, we are pinging to show that the routing tables are valid and that that's working correctly. Another way to compare or classify routing protocols is based upon the 5 characteristics that are shown. First, we need to talk about what convergence is. I don't think we talked about that. Convergence is when every router has a complete and accurate representation of the network. So obviously the faster your network converges, the quicker it's going to be sending packets correctly. So as far as speed of convergence, the first 3 are considered to be slow and the last 3 are considered to be fast. So if fast convergence is an issue, then you would need to pick an appropriate routing protocol. Scalability, how large can your network be? Can you have hundreds, can you have thousands of devices? So the division is kind of the same. The first 3 are good for small networks. If you're going to have a very large network, then you would need to choose one of the latter 3. Variable length subnet mask, all the modern ones like RIP version 1 and IGRP, those were routing protocols before we really had classless subnetting and therefore variable length subnetting mask. So all the newer ones support that. The 2 older ones do not. The next row is resource usage. Basically what resource usage is how much resources on the router does it consume? And those resources are CPU, memory, and bandwidth. The first three are low, enhanced IGRP is medium, and then when we go with the link state protocols, they're going to have high resource usage. And the last is how easy or complex is it to set up and maintain. The first three are really simple to do, and then they declare that the last three are complex in nature. So it's going to take you a little more time to set those up, understand them, and maintain them. Okay, what we're going to talk about now is the metrics that the different routing protocols use. Basically, a metric is a measurement. So it is a value that it uses to figure out how to make routing decisions. So here we have two PCs. We have three routers redundantly formed into a triangle. One of them is a 56K, so a modem, and the other two are T1 lines, which not super fast by today's numbers, but much, much faster than a 56K modem. So what's going to happen is RIP chooses hop count. So to get from this PC to this PC, the quickest way is to go router 1, router 2 to this PC. Now OSPF will choose the best based on bandwidth or speed. So it's going to come across and go router 1, router 3, router 2 into the PC. So that's what the animation will show us. So it chooses the route that gets there the quickest. In the original days when RIP was created, probably all these connections were pretty close to the same speed. So hop count would be almost the same thing as speed, but that's no longer the case. Over in the bottom right of the text, as I said, RIP uses hop count. OSPF uses a cost, which is based on bandwidth. And then Enhanced Interior Gateway Protocol, it uses minimum bandwidth, delay, load, and reliability. So it's actually going to make decisions based upon 4 pieces of information. Okay, 5119 is an activity. Notice down at the bottom that there are 3 different activities. These are going to make sure that you understand some of the concepts related to the different classifications of routing protocols, so you can do those 3 on your own. Here, 51110, we have another activity which is comparing some of the routing protocols between things like speed of convergence and resource usages, things like that. Notice that there are 3 figures down here at the bottom that you can go through and do. Okay, so it is changing the protocols up at the top of this diagram. 51111 is basically, can you match the metrics used to the routing protocol or routing protocols that use that particular metric? So you can do 51111 on your own as well. Okay. Switching to section 5.2. So 5211, dynamic routing protocol operation. So basically it's going to talk about the different things that the router protocol has to do. They're over in the text. It's going to send and receive messages on the various interfaces related to routes. It's going to share messages and routing information that are using the same protocol. Routers are going to exchange information, and based on that information, they will learn information about remote networks and remote routers. And when a topology changes for whatever reason, either a router's added, an interface comes up, or an interface or link goes down, it's going to exchange information with other routers. And as shown in the diagram, it's going to keep track of routing tables. So if I play this animation, the router is going to examine information about itself, and then it's going to send updates out. Other devices will see those updates, and if necessary, make changes to their routing tables. And router 1 did it first. Now router 2 is doing that. Now then, the next page is going to talk about when we power a router on, or when a router loses and regains power. These routing tables are kept in memory. Memory, of course, is volatile. So when a router is powered off, any information, any configuration, any routing tables will be emptied out. So what happens is, this is entitled cold start. When we power it on, we don't really know anything at all about the network. So what we're going to do is we're going to play the animation and look at the text, and this will be what happened when a router initializes. So what's going to happen is they're going to look at all the networks that are directly connected to them, and they're going to put information about those networks in their routing tables. And of course, since these are directly connected interfaces, that's why the hop count is showing up at 0. So that's pretty straightforward. It's just looking at the hardware and the connections and doing the initial population of that routing table. After that, it starts doing something called network discovery, which is where it exchanges updates. These updates are created, they're sent, and they're processed. So what's happening is described over here in the bottom of the text. But if we hit play, they're going to start exchanging updates. So it's going to send out information about all the networks it knows about and the interfaces it uses. So this is the creation of the various routing protocol updates that are going to be sent. So each of these had 2 interfaces, so it's going to build 2 updates. And then these updates are going to be passed around the network. And as they're passed around the network, the information in there is going to be read. It knows how many routers it went through. So notice that these, some of these are being populated with a route count of 1 because they had to pass through 1 router to get to the destination device that's updating its routing table. So at this point, we have a completely updated routing table based upon the 4 networks that we have shown in the diagram at the top. Okay, what happens is after some period of time, new updates are created, what they're calling the next update. They're sent and they're processed. So if we send this, new updates are created. And then once the new updates are created, then all the information is exchanged, and any updates that might be necessary in the routing table are made. So in this case, router 1 and router 3 learned about networks that are at the other end of the topology. Okay, we're talking about convergence again, just to repeat because it's important. Convergence is when all routers have complete and accurate information of the entire network. So what we see here is that our network has now converged and they all know about all 4 networks, and in this case have a hop count to make it to that destination network. Okay, this is a packet tracer activity investigating convergence on routers. I am going to assign PKA 5216, so watch for that to appear in Blackboard. I think this chapter only has 1 packet tracer. I'm not positive. No, actually there's 2. So now what we're going to do is talk about distance vector protocols. So here's the diagram that we saw like on the 2nd page of the chapter. And since we're talking about distance vector routing protocols, it has RIP and EIGRP highlighted because those are the distance vector protocols that we are talking about. If we go to the next screen, it's going to talk about how distance vector algorithm works as far as sending updates and that type of thing. So I'm going to hit play. There are updates that are going to be sent based upon information in the routing table. It's going to then, based on any updates, calculate the new best route to make it to particular networks. And then it is going to keep sending updates to update all the information. It is able to detect when a topology change is made. In this example, 1 network went down, and then what it will do is it will send that update over to router 1 in this case, and then based upon that update, router 1 will update its table, in this case by deleting a network that is no longer reachable. Okay, 5223 is an activity on some of the terminology that we have talked about. So you can go through and do that on your own. 5231 is routing information protocol. Basically what it's doing is, in this case, instead of routing information protocol, what we're talking about, they're talking about RIP, possibly the first routing protocol that existed. So originally, a long time ago, RIP version 1 was created, and they thought that just dealing with the hop count was the best way to figure out the best route to send the packet along. As far as updates, they were simply broadcast. 32-bit IP address with all ones, represented as 255.255.255.255 is the global broadcast address. Of course, broadcast won't pass through routers, but it will go to every host on the local network. By the time version 2 came around, they decided that using a multicast address was going to be better, so that they could just send it to routers. Basically, it's kind of like broadcasting to routers if you set it up correctly. Variable length subnet mask was not around when RIP version 1 came out. It was when 2 came out, so that's incorporated. CIDR, which is the classless routing and representation of subnet mask, was not around during version 1. It is used in version 2. Summarization is the process of basically grouping networks together and sending one update for multiple networks. And then authentication, where you have to authenticate to a router to be able to make updates. That type of thing is supported in version 2 and was not part of RIP version 1. Okay, kind of the same thing for IGRP, followed by enhanced IGRP. So basically, we have a number of things that are used as metrics: bandwidth, delay, reliability, load. Can be included if you want. That is the same in both eIGRP and IGRP. Like with RIP, originally they broadcast everything, and then later they chose a multicast domain to use for eIGRP. And same thing for everything else: variable length subnet mask, CIDR, summarization, authentication. That was not in the first version of this protocol, IGRP. However, it was incorporated into enhanced IGRP. And there's some information over here. I think we've discussed most of it. We'll talk about hello messages in a moment, but you might want to read through that to just refresh your memory and make sure we didn't miss anything. 5233 is an activity that compares RIP and IGRP. Notice that there are two different activities down here. And when you change them, it changes the 5 things that are here in the graphic. So you can do both those activities on your own. 5234 is a packet tracer activity, also on comparing RIP and enhanced IGRP, and dealing particularly with path selection. So I will be assigning that, so watch for that to appear in Blackboard. We'll now move on to something called shortest path first protocols. They are highlighted in the graphic like they were before, like RIP and eIGRP. So in the case of shortest path first, we have OSPF, which its name is Open Shortest Path First, and then IS, intermediate system to intermediate system, are the two that we're going to discuss. Over here, there are commands. Basically, we say router OSFPF and then give some information to enable that. We didn't talk about it, but RIP, you just log in and you say router RIP, and it starts running the RIP protocol. There's no really configuration options, I don't think, that are needed. And then there's a network command that is used to advertise networks when we're using shortest path first protocols. So here we have something called Dijkstra's algorithm, and basically it is just a way to go through and calculate the cost, and then the lowest cost will be considered the shortest path. So the numbers on the diagram are costs associated with taking a particular route. Notice that there seems to be this extraneous 2 everywhere, but that's what it takes to get through the router. So there is a little cost associated with going through the router, a slight delay. So what they're doing is they go through, we'll see this in a moment on the next page, I believe, and for each router they would go through and calculate what they're doing down here at the bottom, the path. So here what would happen is router 1 would need to add up all the cost associated with to make it to router 2, router 3, router 4, and router 5. So they've used the values on the diagram and done it for router 1 to every other router. Here they've done it for router 2, they've done it for router 3, they do it for router 4, and then finally from router 5 they calculated the cost or the distance to all the other networks. So that's how those values are calculated. Now then, what is the actual routing protocol? So each router is first going to learn about routers that are directly connected to it. And then they're going to basically say hello, use a hello packet to discover directly connected networks or directly connected routers. Then they're going to build something called a link state packet that contains the state of each directly connected link. And then what it's going to do is it's going to flood that to all the neighbors, who then store that in their database, and then those will be passed on to other routers down the line. So here we have a network set up, and then basically what's going to happen is as we go through, in this case we're looking at router 1, and then router 1 is going to have information about link 1, this fast 00. It's going to have the network, it's going to have the IP address of the interface, it's going to say that this is an Ethernet network, the cost of the link is 2, and there are no neighbors in this area. So then what it's going to do is it's then going to look at link 2 and gather all the same information for link 2. And then link 3, and then link 4. So it will have to go through and gather all that configuration information so that it knows about all the links and the link states associated with that. Now we talked about hello messages. So basically what happens is if a router is going to discover its neighbors, it's going to send a packet out and basically say, hey, I'm router 1. And if another router gets it, then they're going to respond back and say, hey, I'm router whatever. So that's how it determines, it's kind of like a ping message, if you will. That's how it determines its neighbors. And again, a neighbor is a directly connected device. Okay, as far as building the link state packet, that information is packed up. It's going to have all the information about this device. So that's just showing that we're going to pack it up and send it out. And to send it out, we flood it. So we take that packet and we're going to send it to all the routers, which are going to send it to all the other routers, so that we can gather information about the network. Based upon these LSP packets, what's going to happen is router 1 in this case has a link state database, and it's going to have information about all the links and ways to get to the various other routers and what the cost to get to those routers are, etc. We also have something called an SPF, shortest path first tree, that goes through and basically draws all the connections. So this is the router 1 link states, and then we learn the router 2 link states. Notice that, you know, router 1 only shows the ones that are directly connected. When we add router 2, we have another network over here. When we look at router 3, we learn about that part of the network. When we look at router 4, we learn about that part of the network. And then finally, when we look at router 5, we learn about this portion of the network, this network over here. If we are looking at router 1, based upon this information, it says if you want to make it to one of these particular networks, here's the path that you want to take, and this is the cost associated with the entire path. So that is the ultimate goal, is to have this destination followed by the actual path that we would take to get to that destination. Okay, here in the case of OSPF, we have just a routing table that shows us the shortest path to take and the cost, and then down here would be the complete routing table that we have when we add that to our OSPF routing table. (5329) is an activity related upon building the database and the SPF tree based on a topology with cost shown in these octagons or whatever they are. There are 3 of these, or 3 parts of this, so make sure you do all 3. You can do those on your own. Okay, link state protocols. These are probably the most dynamic because links can be changing in our network. So they're going to talk about advantages and disadvantages and things you need to know about link state protocols. So 5331 starts with the advantage. So each router keeps its own map. So each router is able to tell very quickly what the shortest path to take is. By flooding the LSP packets out router to router, we can get some pretty fast conversions. We can spread that information around. Future LSPs are only sent when there's a change to the topology. I think we saw in RIP that like an update was sent every 30 seconds or something. Well, LSPs can go a really long time if there's no topology change. When there is a topology change, then send an update out. And it's hierarchical design, which usually fits most network designs good. As far as the disadvantage is, we have to build that link state database and the SPF tree, which means we use resources. They mention memory here. I guess next, doing the calculations uses CPU. And then because we are flooding packets out, sending packets out over the network, there is some bandwidth used with that. Hopefully our updates are small enough or infrequent enough that that does not consume a lot of bandwidth. So this is basically showing where we would flood packets and where routers would learn about it. So basically what you do is you can divide these into areas. I think it's kind of funny they have Area 51. But you can divide it into areas so that your LSP flooding only goes to a particular area. And that's usually, going to be within the same cloud. Okay, this is just showing protocols that use link state. We have intermediate system to intermediate system, and it says that it is used by ISPs and global carriers. So that's typically where that is used. We have OSPF version 2 and OSPF version 3. The first is for IP version 4 networks, version 3. The second one is for IP version 6 networks. So, That finishes up Chapter 5. So watch for an announcement for the Chapter 5 chapter exam in netacad.com.